In this video, I will use an example to illustrate how to calculate the maximum and the minimum of a function using derivatives. Here is the example. I want to find the extrema, and perhaps also the local extrema, of the function f defined by f of x equals x cubed minus 3x squared minus 9x plus 35 on the closed interval from minus 4 to 4. I am going to reason in two steps. First, f is continuous on this interval, which includes both endpoints. I can use the extreme value theorem, and I conclude that f must have a maximum and a minimum on this interval. I know some students like to skip this first step, but it is essential. Without it, everything else fails. Second, now that I know there is a maximum and a minimum, they may be at an endpoint or at an interior point. But if they are at an interior point, they must also be local extrema. And then the local extreme value theorem tells me they must be critical points. So I know there are extrema, and I know where to look for them. Here's my plan. And this could work for any continuous function on a closed and bounded interval. Find all the endpoints and critical points. As a reminder, critical points are interior points where the derivative is 0 or does not exist. Compare the function at these points. One of these points must be the maximum, the one with the largest value of f, and one of them must be the minimum, the one with the smallest value of f. That will be it. This bears repeating. The method only works for a continuous function on an interval including both endpoints. Otherwise, the function may not even have a maximum or a minimum, and if I use this method carelessly, I may get the wrong answer. Okay then. Let's perform the calculations for our example. Here is the function again. Finding the endpoints is easy. They are minus 4 and 4. As for the critical points, I need to find out when the derivative is 0. This is a polynomial, so the derivative always exists. The derivative f prime of x equals 3x squared minus 6x minus 9. I can factor a 3. And I can further factor this as x plus 1 times x minus 3. To factor, either guess and check or use the quadratic formula, as you prefer. So the critical points are minus 1 and 3. That's it. That's all the points I need. I have 4 candidate points. To figure out which one is the maximum and which one is the minimum, we evaluate f at them. These are the values. The largest value of f is 40 at x equals minus 1. That must be the maximum. The smallest value of f is minus 41 at x equals minus 4. That must be the minimum. We are done. But this tells us even more about the function. We can guess a sketch of f just from this. Here are the 4 interesting points in a graph. And I know that between any two of them, there are no other critical points. So that suggests what the graph will look like. Something like this. So I am guessing that at minus 1, I also have a local maximum, and at 3, I have a local minimum. Strictly speaking, this final part was not fully rigorous yet, but geometrically it makes perfect sense, and we will learn soon how to argue this more rigorously.